Hello, this video explains the compound Poisson process, which is an example of a hidden Markov chain. At the end of it, you should be able to explain the types of phenomenon that can be modelled using a compound Poisson process, and you should be able to derive expressions for the expectation and variance of a random variable, y of t, which is a function of time, so long as y of t can be described using a compound Poisson process. Let's begin by looking at an example of a phenomenon which requires the compound Poisson process to model. In particular, let's look at this question. Consider the amount of money spent by all the customers of Amazon as a function of time. The value of this quantity at any time is clearly random, as there is no way of predicting what and when each customer will buy. That said, we know that this quantity will always increase, as customers cannot unspend this money. Incidentally, for the purpose of this question, there are no refunds. This is not something we can model using the Markov chains that we have learnt about in other videos. The problem is that customers spend money at random times, and the amount that they spend will be random. And we have not yet learnt of any model that is able to deal with these two types of randomness at the same time. Allow me to explain what I mean here with an example. Suppose that the future pans out as follows. The arrow here represents the direction of time. We then have various events that occur on the Amazon website as customers buy items. So, for example, at this time, Mr. Smith buys a copy of Middlemarch by George Eliot. At this later time, Mrs. Jones buys a Coldplay album. A considerable time passes, and then Mrs. Harrison buys a Kindle. Shortly after Mrs. Harrison is done, Mrs. Mills buys a new pair of shoes. There is then a long wait before Mr. Parks buys a Superman DVD, and lastly, Mr. Patel buys a camera. If we think about this from the point of view of Amazon, these people's purchases arrived at random times. Amazon has no reason to know why these people are in need of these particular items at these particular times. We have learned to deal with processes that occur at random times, however. We can model a counting process, in this case a model that counts the number of purchases, using a Poisson process. Why is this not sufficient here? Well, the answer to this is that we are interested in the total amount of money spent. The items the various people shown here have bought most definitely don't cost the same amounts of money. Some of these items are very cheap, while others are considerably more expensive. For instance, the novel probably will cost around £8 or so, the album £10, the Kindle £100, the shoes maybe £60, the DVD £15, and the camera £160. If we were given all the amounts of money spent, in other words, if we were just told that 6 purchases had been made from the Amazon website, we could assume that these were random variables generated from some unknown probability distribution. We know, however, that as long as this distribution has a finite expectation and variance, we can use the law of large numbers and the central limit theorem to calculate an approximate expectation for the distribution. Our problem is only that we want to have a measure of the total amount of money spent as a function of time. The fact that each customer spends a random amount is not a problem per se. Let's summarize then. Purchases arrive at random time, and we can thus model the number of purchases by time t using a Poisson process. Furthermore, the amount spent by the customer in each purchase is random. We are going to assume, however, that the amount spent during each purchase represents the generation of a random variable, and that all these random variables are identically distributed, so that we can exploit the law of large numbers and the central limit theorem. The question that we will seek to answer in this video is thus, can these two ideas be combined so that we can create a model that we can use to describe the total amount spent as a function of time? The answer to this is a clear yes. The stochastic process in question is known as the compound Poisson process, which we will now learn about. The key piece of theory for understanding the compound Poisson process is the conditional expectation theorem. The way this theorem is used is that we calculate the expectation of the total amount spent by time t, a random variable that we call capital Y of t, by conditioning on the number of purchases n of t that have occurred by that time, as shown in this formula. Let's look at the conditional expectation values that we have to calculate here first. The expectation of y of t, given n of t is equal to n, is just the expected value of y of t, the amount spent, given that exactly n purchases have been made. Calculating this expectation value is straightforward. In each purchase, a random amount of money is spent, but we have assumed that the distributions underlying all these random variables are identical. We call the expectation of this distribution mu. The expectation of the sum of n of these independent random variables is thus simply n times mu, as the expectation operator is a linear operator. Let's now turn to the probability. This is the probability that exactly n purchases have been made. As we discussed in the previous slide, we can model the arrival times of the purchases using a Poisson process. This Pn of t equals n is the probability that exactly n events have occurred by time t, which we can calculate using the formula we derived when we studied the Poisson random variable. Inserting these two formulae into the sum, we find the following. We can simplify this expression by taking various constant terms outside the summation. Notice that in doing this particular simplification, we have cancelled the n from the numerator and the denominator, hence the n minus 1 factorial in the denominator, in the new expression. Furthermore, for reasons that will become apparent in a moment, we have decreased the power of lambda t by 1 and taken a lambda t outside the summation. In the next step, we change the variable we are summing over and replace n by y, where y is equal to n minus 1. This changes the bottom limit of the sum from n equals 1 to y equals 0. The reason for doing this should become apparent when you see what is inside the new summation. This new sum should be familiar, as it is simply the Maclaurin expansion of the exponential function. In other words, this sum is equal to e to the plus lambda t. This factor of e to the plus lambda t cancels with the factor of e to the minus lambda t that we took out in the previous step. The final expectation is thus mu times lambda times t. In other words, by time t, we would expect the customers to have spent mu times lambda times t on buying various things from Amazon.com. We can calculate the variance for the compound Poisson process in a similar way. The proof here is somewhat more involved, but we are at heart still just using the conditional expectation theorem. In other words, the convolutedness of the proof here comes about because the algebra is a little involved. The underlying mathematics and basic method is just the same as the maths we used for the expectation. In the next few slides, we will go through this proof. As we do so, however, remember that the most important step is the one shown here. In other words, the most important step involves calculating the expectation value using the conditional expectation theorem shown here. What we are calculating here is the expectation of y of t squared. Remember, y of t is a random variable that tells us the amount spent by time t. We need to calculate this expectation as the expectation of y of t squared minus the expectation of y of t all squared is equal to the variance. As stated previously, we are calculating this expectation of y of t squared using the conditional expectation, just as we did previously when we were calculating the expectation of y of t. The probability that n of t is equal to n here is straightforward to determine. This is just the probability that exactly small n events have happened by time t. As was discussed when we were looking at the expectation, this we can calculate using the expressions we derived when we were looking at the Poisson process, as shown here. The slightly more difficult part of this expression is the conditional expectation of y of t squared, given that there have been exactly n events. Y of t will be the sum of n independent and identically distributed random variables, and y of t squared is thus the sum squared shown here. Expanding out this bracket, we get the following sum. We can now take the expectation of this sum and exploit the linearity of the expectation operator to give the following. Now notice that each of the random variables we generate, the capital X's, are independent. This is useful as the independence of these random variables ensures that we can write all the expectation of x1, x2 terms as the products of an expectation of x1 multiplied by an expectation of x2, as shown here. It gets better, however, as all these random variables are identical. They have the same underlying cumulative probability distribution functions. This ensures that the value of the expectation shown here are identical, and that we can write the product of ex1 and x2 as ex all squared. Furthermore, as we generated this sum by multiplying out the square of n terms inside a bracket, we know that there are exactly n terms like this, and n multiplied by n minus 1 terms like these later ones. The expectation of y of t, given that n of t equals n, is thus equal to n multiplied by the expectation of x squared plus n multiplied by n minus 1 multiplied by the expectation of x all squared, as shown here. We can insert the expression we have just derived for the expectation of y of t, given n of t equals n, into the conditional expectation theorem as shown here. Before we do so, it is worth exploiting the other information that we were given in the statement of the problem. In particular, we were told that every time someone buys something on Amazon, the amount they spend is given by a random variable, capital X, with expectation mu and variance sigma squared, as shown here. We can thus replace the expectation of X terms by mu immediately. We can also use these facts to write the expectation of x squared in terms of mu and sigma. Remember, we know that the variance is equal to the expectation of x squared minus the expectation of x all squared. Furthermore, the expectation of x all squared is just equal to mu squared. By rearranging this expression, and by using the fact that the variance is equal to sigma squared, we can thus write that the expectation of x squared is equal to sigma squared plus mu squared. Inserting all of this into our expression for the expectation of y of t given n of t, and multiplying out all the brackets gives the expression shown here. We immediately see that the n mu squared and minus n mu squared terms cancel here. This leaves us with a relatively compact expression for the conditional expectation. Inserting this into the conditional expectation theorem gives the following. Taking out constant factors of the sums, we are left now with this. Notice that the first of these summations contains the value of n, the number of events, multiplied by the probability of having n events. This is just the expectation of a Poisson process. The second summation, meanwhile, contains the square of the number of events multiplied by the probability of having n events. This is just the second moment of the Poisson process. In other words, our expectation for the expectation of y of t squared can be simplified to the following expression. This expression is written in terms of mu, the expectation for the amount of money spent in each transaction, sigma, the variance of the amount of money spent in each transaction, the expectation of n of t, which is the expectation of the Poisson process, and the expectation of n of t squared, which is the second moment of the Poisson process. We continue by remembering we would like the variance, which is given by the following expression. We have everything we need here. We have just shown that the expectation of y of t squared is equal to sigma squared times the expectation of n of t plus mu squared times the expectation of n of t all squared. Furthermore, in the early parts of this video, we saw that the expectation of y of t was equal to mu times lambda times t. For purposes that will become clear in a moment, we are going to rewrite this expression as mu of t times the expectation of n of t, which is justifiable as the expectation of the Poisson process, the expectation of n of t, is equal to lambda t. Inserting all this into our expression for the variance gives us the following, which we can rewrite as shown here. Now notice that the expression inside the bracket, the expectation of n of t squared minus the expectation of n of t all squared, is just the variance of the Poisson process, i.e. this is the variance of n of t. So our expression is just sigma squared times the expectation of n of t plus mu squared multiplied by the variance of n of t. Furthermore, the expectation of n of t equals the variance of n of t, as these quantities are both equal to lambda t, as n of t is a Poisson process. We thus arrive at the final expression for the variance shown at the bottom of the slide. The proof that we have just gone through is rather long. It is, however, relatively straightforward. The difficult bit is the first part, where you write out an expression for the expectation of y of t squared using the conditional expectation theorem. The rest is then just a lot of algebra and manipulation of equations that is not particularly challenging. To conclude then, the learning outcomes for this video were the following. You should be able to explain the types of phenomenon that can be modelled using a compound Poisson process, and you should be able to derive expressions for the expectation and variance of a random variable y of t as a function of time if y of t can be described using a compound Poisson process. Hopefully, you at least now understand why the compound Poisson process is useful and what it can be used to model. On the proofs, you may need to watch the video again to get all the details in your head. You have hopefully seen, however, that these proofs involve nothing more complicated than an application of the conditional expectation theorem that we have seen before. If you are happy with what has been covered in this video, there is now a programming exercise on the compound Poisson process that will get you to think about this a little more. Thank you for your attention.